So we need to understand the basis of it and how signals are treated in the digital world and what are the consequences of having digital signals instead of analogous signals. Okay, and you see that there's a strong difference in a way that you can do processing. Okay. So before jumping in, so my name is David Gaillot, I'm a professor here at the University of Lille, and my field of expertise is signal processing and wireless communications. Okay. So that's the easy key in Moodle. Alright, so you have two ways of accessing Moodle. In the main page of Moodle, there is some room where you can put the key and you will access directly to the class without searching for it. Second option, you search for the class and then there is another key which is different. So that's the easy key, it's easier like this. Okay, main page, you look for the key, access, you type it in, and you will access the class. So in Moodle, you will have access to the handouts and also some materials that we will be using for the lab work. Okay. All right. So that's the syllabus of this class. So we'll be together 36 hours. That's okay. So it's 18 hours of classes. So it's 9 slots of 2 hours. Okay. And the first 2 chapters that I will treat is dedicated to introduction to signal processing, of course, sampling, quantification, and then I also treat some other theorems and digital filtering. Okay. And then starting at the end of October, it's just a few days before the holidays actually, that will be the first lab work. Okay. So the lab work will be where you were this morning in the same class. Okay. Just for your information, my office, just across. Okay. So just across the exit, you have one door, and this is my office. Okay. So we'll have 4 slots of 4 hours and 1 slot of 2 hours. But depending upon your advancement, we'll see how it goes. Okay. The purpose of the lab works is just to have hands-on experience with signal processing to understand it, okay, and manipulate the software that can do sampling, quantification, digital filtering, etc., correlation, convolution, things like that. Okay, maybe some of you guys are familiar with MATLAB.
Yes.
Yeah. How many of you have ever used MATLAB? Almost all of you, right? You never used MATLAB?
Yeah.
Yeah.
Because I have a base in neuroscience.
Okay. So sound good. Okay. So we for your information, we have a campus-wide MATLAB license, meaning that as an enrolled Lille student, it's free for you. Okay. So if you go to the MathWorks website and you log in using your Univ login, it will automatically transfer the registration process to the main ULIL page. When you do this, you will be automatically being created an account in MathWorks. Okay, and from that point of view, you will be accessing the MATLAB tool for free with all the toolboxes. Okay. And second of all, you can also access MATLAB online. So that means you can use it anywhere without having the software on the machine. Okay, so that's quite convenient. Okay. So right now the labs, they're written in Scilab. Scilab is like the French version of MATLAB, the free version, the original free version of MATLAB. Okay. So if you guys all use the MATLAB tool, I think I'll transfer to MATLAB. It's going to be easier anyway. Okay, so let's see that. Right. Anyway. And all the examples that I will be presenting throughout the classes will be using MATLAB anyway. Right. So let's talk about the evaluation of the module. So it's 30% the final exam, Okay, you have 2 sessions for the final exam, like I would say all the courses that you have, and you have 30% of tests. For the test, so you will have quiz in classes, okay, 1 or 2, depending on how much we advance, okay, and you also have an exam on MATLAB or Scala, okay, individual session where you will have to answer theoretical and practical questions on MATLAB. Sounds good? So I'll get the attendance list. If you get it filled in. Okay. Right. So what I'm going to do is call your name, because I don't know you, so I need to put a name on the face. Okay. So Abbas, Aslam, Awada, Boui.
Oui.
That's how you spell it. Okay. Ibrahim, Khalid, Moutain, Servout, Tariq, Nakli, and Patwari. It's enough. Okay, Patwari. Okay. Thank you. Okay, so this is the content of this class. And so again, you come from different backgrounds. So it's mostly reminders for those of you who already took some signal processing classes. So I'll talk in the first chapter, I'll talk about signal and noise. That's a typical thing you need to understand. I talk also about signal classification. And of course, the things you never like, Fourier series and Fourier transforms. Nobody likes it. But the thing is, it's being used broadly, widely, everywhere, even now, inside your smartphone. Your smartphone is doing Fourier transform like crazy. Okay? That's anything but it does. Wi-Fi, 4G, 5G, it's Fourier transform. Okay. Autocorrelation, correlation, and color spectral density, it's just for signal analysis. Okay? But this is quite powerful techniques when it comes to signal processing. And again, this is being used. You use it all the time. You access your phone with your face, it's correlation. Okay. Face recognition, it's correlation. Okay. Speech recognition, it's correlation. So all the tools you've been using with your smartphone nowadays, it's nothing but this. Okay. So I'll try to give you the basics of it, just so you understand. All right. So if you have any questions throughout the class, just stop. Okay? So raise your hand, ask me the question. Okay, we can have a discussion and then move on. Alright? So do not hesitate. If you have a specific question about the class, okay, you can either talk to me after the class or you can send me an email. I forgot to tell you that. If you need to have a rendezvous with me, for example, okay, just send me an email using your unique email address. Okay? So try to be professional on that. And quite fast to reply to students. Alright. So what is digital signal processing? I try to be insistent on the fact that it's digital. Okay? Because signal processing is a wider topic. Okay? So digital is a subtopic of signal processing. So it refers to the processing, so it's a mathematical operation. I know you don't like to hear that. But that's what it is. Okay? It's performed on a digital signal. Okay? So it's already bits. Okay? Generally with the goal of either extracting or manipulating the information stored on the signal. So right now, if you go on websites or on social networks, you can see zillions of pictures being manipulated, with AI line, whatever. This is nothing but signal processing. So DSP, so digital signal processing, is ubiquitous. Do you know what that means? Have you heard that term before? Ubiquitous? No? Okay. Ubiquitous means it's everywhere, every time. Okay. So in fact it's attached to you. And that's what it is with your smartphone, right? That's what it is nowadays. Okay? You're the generation living every day of your life right now with internet on your left side, on your left hand. That's what it is. Okay? So you have it in your car, on your smartphone, on your TV, on your watch. Some may have it on the glasses. Okay? Alright, so it's everywhere. So we have Wi-Fi right now, everything is connected. Okay? I mean, your phone connects to Wi-Fi or 4G or 5G. It's completely smooth to you. Okay? Alright. So that's what it means to be ubiquitous. Okay. So it can be applied to a wide range of applications. Okay? Filtering. So what is filtering? What does that mean for you, filtering?
To reduce the noise and other things from the signal, to make it more smoother to hear the information.
Yeah.
To cut whatever we don't want to shoot from specific thing.
Yeah, exactly. That's the most basic operation that you do. Remove noise or remove components that you're not interested in. Okay? Compression. What is compression?
Compression means to
one at a time.
Maybe if the signal length is very large, then compressing it can be an easier form.
Yes, that's what it is. So when you go online, you go on YouTube or you watch a video, it's compressed. Okay, and the raw stream is extremely large. Like depending on the original resolution, it can be so large it cannot fit into the bandwidth of your device. It's impossible. So you need to compress it depending on the application. So of course, depending on the application, the compression could be so rough that sometimes the quality is not there. This is what happens when you look at low quality videos on YouTube because it's been compressed so much. When you look at DVB, digital video broadcasting, okay, it's compressed. Everything is compressed. It's right now on your phone. It's almost impossible to have any streams, voice, data, video, whatever, that is not being compressed. It has to be, otherwise it's impossible. Okay? So denoising, of course, you have noise everywhere. Okay? So right now, for example, I have the noise of the video projector. It's small. Okay? So it's trackable. But it is there, so we have to live with it. Okay? Radar applications, okay, could be radars for civil planes, okay, could be for boats, for anything, for cars, for example. Okay? Now we have radars everywhere in cars. Okay, so that's what's being used. So you have signal processing in your cars. Speech recognition, you know that. Okay. And of course, video and audio coding and coding. I talked about that when it came to compression. So the highest benefits of DSP comes from the flexibility compared to analog signal processing. And I'll talk a little bit about it later, but it's just because analog signals, they have an infinite bandwidth. Okay? So it's like you were trying to treat information that is infinite when it comes to analog. So it's very difficult depending on the nature of the signal. However, when it comes to digital, the stream of the data is much smaller because you have a smaller bandwidth. Okay, so it's easier to treat with the hardware and software platforms that we have. Okay. Nonetheless, if you want to do digital signal processing, you will need an active computing element, something that does math. Okay, computing. So, and it's called a digital signal processor, a DSP. So you have to distinguish between digital signal processing, which is the topic, and the hardware that implements it, which is the DSP, digital signal processor. So you have DSP in your phones, you have DSP in your watches. Everything that needs signal processing, you have some kind of DSP inside. Could be light, could be very complex. Okay, if you buy a PS5, it's very complex. Okay, if you buy the video processing cards that are being used right now from NVIDIA for AI, it's really complex. It's but nothing but fast. Okay, but it's pretty fast. And that's what we need. Okay, so let's jump to signal classification. Okay. So here, what is a signal? Okay, so it's a variable. So again, I go back to that. Okay, for us engineers, scientists, it's typically depending on always. It is space, but sometimes more. I mean, most of the time it's time. Okay, it always contains information about a phenomenon. Could be anything. Sound wave, like a phone ring, light, traffic lights, okay, being examples of sound. Okay, you can find many examples of signals. When I speak, it's a signal because it carries information.
Yes.
Okay. If I say it brings no information, it's useless for you guys. Just know. Okay. So again, for us in electronics specifically, we'll be talking about electrical signals, right? I mean, that's typical signal that we deal every day, right? So it could be voltage, it could be currents, power. More generally, could be an electromagnetic wave. Okay. And these signals will carry information. Okay. If there is no information, it's not a signal. Okay, you can call it signal, but there is no information. Okay. So again, could be like this example, could be a function of space, like an image, carrying information. Okay. So this is just an example of a time varying signal. It's just an example, completely arbitrary. And what I add to this signal is noise. Okay. And noise, what it is? It's an irregular fluctuation that is accompanying the signal, and it also fluctuates randomly over time. Okay. But it's not part of it. It tends to obscure it. Okay? Like right now I speak, this is a signal. And the sound of the video projector is the noise. So right now the noise is small. Okay? But if the noise gets larger, I will have to speak louder. So I have to boost the power of the signal. Okay? And that brings me to an important aspect of digital signal processing. It's called signal to noise ratio, the SNR. Okay? So the SNR, so you have two ways of two notations, S/N or SNR. Okay? It measures the amount of noise in a signal. Right? So let's say I have a signal, it has a given power. Okay? And then you add some noise, you also have some power. So, I mean, it's straightforward that the total power is the sum of the power of the signal and the power of the noise. Okay? And PS here is the useful signal. Okay? So I make a distinction between the signal and the useful signal. The useful signal carries the information. Okay? The signal carries information and noise. So my voice is the useful information, but what you hear is my voice, the useful information, and the noise. Okay, that's what it is. Okay. So the SNR, so it's signal to noise ratio. It's the power of the useful signal divided by the power of the noise. Very simple to understand. Okay. Of course, if you substitute PS by PT minus PN, this is what you obtain with the total power. Okay. The problem is, in terms of signal processing, is you measure what you hear is noise and my voice. Okay, so your brain, it has to distinguish from my voice and noise. So right now I can do that operation because the noise is very low. But if you are in a very noisy environment, like a concert, for example, or a noisy restaurant, sometimes you know it's difficult to understand. Okay, because it's very noisy. Okay, so the SNR is very low when it's very noisy because the power of the noise is very large. And the power of the useful signal is very large with respect to the noise, like here, for example. Okay, the SNR is very large. Okay, so for your phone, it's the same. Okay, the signal that is received, okay, it needs to have a certain SNR so it can extract the information. Okay, so that's quite the first, I would say, critical parameter when it comes to signals. You need to know the SNR. Okay, and you have some techniques to extract the noise from the useful signal and denoising the signal. That's also possible. Okay, so the unit that is being used is decibel. Okay, dB. Okay, so the way it is computed is just a 10 log 10 of PS divided by P. Okay, so it can be in dB. Are you guys familiar with dB? Yeah?
Yeah.
Yeah? What about dBm? No. No dBm. Okay. So I'm going to be talking about that because, all right. So as you can see here, it's a ratio. So it's unitless. Okay? dB is unitless. I mean, you can divide a voltage by a voltage. It's going to be dB, but unitless. Okay? If it's amps divided by amps, it's going to be dB, but it's unitless. Okay? So dB, it's a ratio. Just keep that in mind. But then the engineers, because they were fed up with using very low power systems, they introduced dBm. And dBm, it's a power. So it has a unit. It's watt. Okay? So why did we use that? We used the log scale to introduce very small amount of power. Okay? So 0 dBm, and dBm means milli. Okay? Is equal to, do you know that? 1 million. Okay? 1 milliwatt. So this is the power. Okay. So now when it comes to dB, okay, every time you multiply the ratio by 2, you add 3 dB. Okay? So an example. So this is what is being written here. Plus 3 dB is a factor of 2. So 10 log 10 of 2 equals 3. Okay? If you multiply it by 2, you add 3 more dBs. So that's the way we do it. Okay? Now, if you multiply by 10, it's plus 10. If we multiply by 20, it's like you're multiplying by plus 20 dB. Okay? It's a gain. Okay? So if you multiply by plus 30 dB. Okay? You good on that? Yes.
It's only for even?
It's only?
For even numbers?
No.
Odd number also?
Could be completely arbitrary.
Oh.
Yeah. It's a log. You can compute the log of any number, right? So this is just the rough typical number that we use because it's easy.
Okay.
We basically say that the signal has a good quality if the SNR is about 20 dB. Okay? So 20 dB means that the power of the useful signal is 100 times stronger than the power of the noise. And I'll show you some examples. Okay? Right. So now we go back to power. Okay? So because it's a log scale, if I have 10 dBm, so you added 10 dBm, but it's also a ratio. So actually you added 10 dB because it's a ratio. It's like you have multiplied the power by 10, and because you multiply, it's a ratio. So you add 10 dB. Okay? So you add 10 dB and you take 10 dBm. So the power is going to be 10 milliwatts. Okay? You multiply by 10. So if you do 13 dBm, you have added 3 dB from here. So you multiply by how much? 2. By 2. So it's equal to 20 milliwatts. Okay. All right. And 30 dBm, it's 1 watt. Okay? So why do we use that scale? What do you think is the reference signal power that your smartphone receives right now to be connected to 4G, Wi-Fi, 5G, whatever? Do you know that? No? Okay. So you have actually the information in your phone. It's somewhere hidden in the SIM parameter. Okay? So if you go to the SIM parameter somewhere, if I look at my phone, so the SIM, okay. The signals I'm receiving right now for 4G is hear that. That's what I'm receiving right now on my phone. So how many watts is that? So 0 dBm is 1 milliwatt. Okay? Minus 10 dBm is 10 times less. Okay?
Okay, so it's 100 microwatt? No?
Minus 100.
Yep.
Oh.
So you're on the order of femtowatts. That's what you receive right now on your phones. Femtowatts. Okay? It's nothing. Okay? Femtowatts. But that's how it works out. Okay? So I'll give you some examples in MATLAB. sinus function, okay, with a given frequency, doesn't really matter, okay, and I did some noise with an SNR ranging from -10 to 30 dB. Okay, so -10 dB means the noise power is 10 times stronger than the useful signal. Okay, 30 dB means the useful signal is 1,000 times stronger than the noise. Okay, so depending on the whenever it's negative,
It's the noise.
the noise is stronger. When it's positive, the useful signal is stronger. Okay? So you have to be careful with that, because here it's a power. And it's negative because it's very, very small. Okay? This is why you have to be very careful when using dBm and dB. Okay? There you go. So I took the sinus between 1 and -1, sinus, with a given frequency that doesn't really matter, so it's in blue. And here you have the noise. It's random noise. Okay, we'll go back to what means random later on. Okay, but it's random. If I add the red and the blue, the blue signal with the noise, you obtain the red. So it's signal and noise. So if I just give you the red, you have absolutely no idea that there is a sinus behind. Okay? Because the noise is so strong. Okay? So what happens when the noise power gets down? So -9, -8, 7. And you start seeing some trend line. So you see it starts doing this, but it's very shaky because it's completely polluted by noise. Okay? Alright? And then we go to 0 dB. 0 dB means the power of the noise is the same as the power of the useful signal. Same quantity. Okay? But you see that it is a sinus, so it's shaky. Okay? It's noisy. And then I start increasing the SNR. Then dB. So power of the useful signal is 10 times the power of the noise. Okay? So now it's a sine. Right? It's still positive, but it's alright. I mean, you can tell it's a sine. Okay? And you can see that visually the amplitude of the noise is different. This will get smaller too. Okay? So now we go to 20 dB. So now the power of the useful signal is 100 times stronger than the noise. Okay? It almost looks like the original signal without noise, but still, I mean, there's still some small fluctuation. Okay? And if I go to 30 dB, that's what we're doing. Okay? It's almost the same signal. Okay? There's still some difference, but it's very small. Okay? So what I present to you here is kind of an equivalent of an analogous signals. Okay? Like you have an infinite amount of points visually. Okay? Exactly. But it's digital, right? I mean, it's in the machine. Okay? Any questions on that? With respect to dB, dBm, it's clear. I mean, you have to convince yourself if you just apply this log operation with 10, 20, 30, whatever, and you see differences. But again, dB is a ratio showed in class, dBm is the power. So for Wi-Fi, actually, the maximum output power for Wi-Fi is strictly limited. Okay, it's about minus 10, 0 dBm. Okay, so 100, it's 100 microwatt or 1 milliwatt, maximum output power. For your phone, do you know what the max power of your phone is? Do you know that in terms of immediate power? 2 watts. So 2 watts. So it's this multiplied by 2. So you add how much dB? 60. Multiplied by 2. 3. So you have 3 dB. So the power emitted by your phone is 33 dBm. Okay. Okay. So why do we need to master the power quantities? Because right now everything is about IoT. Okay. And IoT you need batteries. You need batteries to power the screens, signal processing, the radio, any functions that you could have on the device itself. Okay? So the batteries that you have right now in your phone, they're quite large batteries. Okay? Going from 2,000 to 5,000 milliamps per hour, depending on the technology that you have. Okay? Why? Because your phone, it consumes a lot of energy. Okay? Do you know what is the main item on your phone that consumes energy?
Microprocessor.
Nope.
Screen. Yes.
The screen. The display. Okay? This is why having larger phones means you need a lot of batteries. When Apple came out with the iPhone, they were very small. And there was a reason for that. Because they knew that if they had to go to larger screens, they had an issue with batteries. And they didn't want the customer to charge the phone twice a day. Which is basically what we do now. Okay? So again, the larger the signal processing is, okay, the more it will consume. Okay? So when it comes to IoT designing, it's quite important to mastering how much is being spent. Okay? And this is something that we come back to you in other lectures, I guess. Okay? Alright. Now we'll talk about signal classification. Okay. So I think it should be clear in your mind. Okay? Because we use very simple concept, but this classification is something that you should think straight. Okay? So a continuous signal, what it is? It's a signal that is time continuous and it contains an infinite amount of value, okay, in the time axis. And for each infinite value in the time axis, we have a value in the y-axis. Could be power, could be voltage, could be n. Okay? So it's infinite. So even if you zoom in, you still have points. Okay? And then this is different from the discrete signal. So the discrete signal is obtained by sampling, and that term is quite precise, sampling, okay, a continuous signal. Sampling is like you select points along the time axis or different axis, whatever. Okay. Okay. So typically what we do in the way we process things, we have values at equally spaced intervals along the time axis. Okay? And actually, if I go back to my MATLAB code and I show you this time, and I zoom in, you will see the points.
Yeah.
Okay? Just to be fair with you, because it's already digital. Okay? So discrete signal is like you select something that is infinite, and you say, I cannot process that, and you have to sub-select information. But that's a problem, if you think about it. Because, say, what's the penalty of selecting points within a space that is infinite? You should have a penalty for doing that. And we see that. The consequences of sampling a continuous signal. But then again, we're kind of safe, and we'll see that also later, because we always deal with periodic signals. Okay? The nice thing about periodic signals is it completes a pattern that is repeatable. So you don't have to evaluate the signal for the infinite time. You just need to evaluate the signal during a period. And that's it. Okay, so that truncates the length of the signal to a small one. Okay? And then we move on to a deterministic signal. Okay? So a deterministic signal is a well-defined signal at any time, and it is represented by a function, like a sine, a cosine, whatever. Okay? So a deterministic signal could be or could not be periodic. Like a sine is periodic, okay, but the exponential is not periodic. Okay. And then finally, we have the non-deterministic signal. Okay, so that's the opposite of deterministic.
Random.
Like the random function. Okay? Random means if I give you a random signal, there is not a single deterministic function that can give you the exact values for all the things above. That's a sheer definition of non-deterministic. It's really statistic. Okay? So this is why we also call them random signals, really random. Okay? And typically, what we do in terms of signal processing, we characterize it by higher order statistics, the mean, the variance, the kurtosis, etc., distributions. Okay. So, if you record the noise from the video projector, okay, and you process it over time, statistically, it's going to be a random noise. And more specifically, it's going to be a Gaussian noise. Okay? And we also deal with Gaussian noise. So I'll give you some examples. Yes?
So the continuous signal is an analog signal?
Yes.
And the discrete one is the digital?
Exactly.
This is digital? This is
Surprisingly, you know, you see me, you hear me, you can touch the table, you can hear. Okay? This is your brain doing the magic. Okay? Your brain is nothing but electrical signals. That's it. You see the world that we live in just electrical signals. Okay? If you disrupt the way the signal transit in your brain and communicate with your body, you lose that. You will use definitely that. But it's continuous because we are bio-livings. Okay? It's fully continuous. But it is slow. The brain is slow. Okay? You have to buy to that. Okay? But because it is slow, it is efficient in terms of energy. You can do lots of stuff during the brain without much of energy. You can even treat information, a lot of information, for multiple days without eating. So you can imagine an IoT device doing just that. Okay? So that tells you how powerful your brain is to treat information. And all the techniques that are being developed right now, in terms of digital signal processing, is trying to mimic the way the brain does things. AI is basically a technique that tries to mimic the way the neurons communicate in the brain, try to process information. Okay. So I'll show you some classical signals. Okay. So this is a trick to the eye. Okay. This is an example of the 20 hertz continuous signal. Okay. So 20 hertz. The period is 1 over 20. Okay, so it's 50 milliseconds. Okay, so we have the 50 milliseconds period. You can see that. Okay, so this is the pattern, and every 50 milliseconds you repeat. Okay. And then you have the same. This is discrete. So only half points. Okay, but as I told you, it's a trick. Why? Because that signal was generated in machines, so it's already digital. So the trick to the eye is what? Connecting the dots. That's how it does. So this is the same figure. This is the same values. The only thing that changes is the representation. Here I use dots in MATLAB, and here I use lines in MATLAB. But this is the same signal. So it's a trick to the eye. Okay? When you watch your smartphone, it's also a trick to the eye. Because when you zoom in, actually you have pixels. Individual pixels that are about the order of 10 to 20 microns. Each pixel is a different color. I mean, it's a triplet actually. Okay? Right? But it's so small that your eye can't see it. Okay? It's very small. But actually, and this is funny, if you look at the screen, you see squares. Do you see the small squares?
No.
Okay? These are the pixels of the video projectors. So you can see the individual pixels, but the light processor on the video projector is very small. But because of the optics, it's like you are zooming in on the light processor. Okay? So now you can see the pixels. But if you're too far away, you can't see them. Because you don't have enough resolution in your eye to see it. Or if you're like me, you can't see nothing without your glasses. Okay? So you can see the different pixels, and the number of pixels give you the resolution of your image. Okay. The first generation of smartphones, they have very poor resolution. Yeah. But the battery would end or not. I mean, my first one would, I would recharge it once a month.
Nokia.
That's it. Okay? But the screen was like this. Okay?
Everyone has some money.
Yeah, it was just black and white, very simple screen. But nowadays, the screens have different, very high-end resolutions. I mean, depending on the quality of your phone, of course. Okay. And so, of course, this consumes more energy. Okay. If you go to an electronic store and you look at a very large TV, okay, HD TV, 2K, 4K, okay. If you get closer to the screens, you will see the pixels.
Yeah.
Okay. Okay. So that brings me to how many points do we have to select in the continuous signal to make it like a signal, like a discrete signal. Here you see I took a point so that the rays close to each other. Okay? And visually it looked like a sinus. Okay? And we'll see later in the labs course that we don't need to take that many courses, that many points. It's useless. Okay? We'll see why. But this is a discrete signal. Yeah?
How many sampling points in this example you have taken?
What did I take? I took 128 points.
For the complete set.
Yeah, for the complete set. Yeah. So that means if you have 20 years, so it's 50 milliseconds, and I took a sampling time of 1 millisecond. So in okay. So over a period, you have 50 points. And then you can have complex periodic signal. So this. So why is it complex? It doesn't look like complex, but it is. Okay, and we'll see later why. Okay, but it's a much more complex signal than the sinus signal. Okay. And the reason why is, if you look at this, it looks like a cosine. Okay. And we'll see later that by adding cosines with different frequencies, we obtain this. Okay? And doing the opposite operation, separating the signal into cosine, is called Fourier series or Fourier transform. Okay. Depending on the domain of application. Alright, so this is a complex signal. It's still periodic, okay? And here it's, again, it's a trick to the eye, it's analogous. Okay. And then you have pseudo-periodic signals. See that? There you go. And this is a pseudo-periodic signal. Okay. What it is, it's an ECG. Do you know what is an ECG?
Yes.
So electrocardiogram, right? Okay. If you measure the bit rate, this is what you will obtain. Okay. And the heart is like the clock of your body. Okay. So if you think about a CPU in a computer or in a smartphone, the CPU has a bit rate. It repeats. It's a pure sinus in the CPU. But the frequency can change in the CPU depending on the task. Okay? If I do nothing, okay, my frequency, my heartbeat is low. Okay? If I walk, if I run, okay, if I'm stressed for any reasons, my heartbeat will go up. Like in the CPU, the frequency will change. Okay? It's never fixed. So depending on the application, it will change from low to high or from high to low. So if there's a high frequency, of course you will consume more. Okay. If you have a low frequency, you will consume less. Right. So why is it pseudo-periodic? And it's just an example here. It's because on a small time, it looks like it's periodic. But actually, if you look at a longer scale, it's not. Okay, so if you zoom in on a small window, it is periodic, but maybe if I display another window, it's not the same. Okay, so it's periodic for a small time. For a small time. So it's pseudo-periodic. Okay. So that means the period of the signal will change over time. Or the frequency of the signal will change over time. That's what it means. The heartbeat rate is pseudo-periodic. And then you have transient signals. So that's a damped signal. Like you drive your car, you have a bump on the road, and the car is doing this, it stabilizes, that's what it is. Okay? So that can be deterministic, or that can be random. But typically it's deterministic. And then you have random signals. So random signals are very funny. This is a random signal. Okay? It's a lot of observations of why random signal. And what it is, it's a coin flip.
It's not the state signal?
Yes. So since it's a coin flip, only two possibilities, head or tail. Okay? So in my case, it's +1 or -1. Okay? So again, you see lines, because it's a trick to the eye. I connected all the points with the line. Okay? But then it's nothing but -1 and 1. Okay? It's purely random. Yeah.
Okay, and value is undeterministic.
It's random, so it's non-deterministic.
Non-deterministic.
Yeah. Because if there is no equation that can give you exactly what's going to be -1 or 1 or for here or here, or it's impossible. It's random. You know, it's like kids. When you have a kid, okay, it could be a girl, or it could be a male.
So
If you have a male.
every non-deterministic signal, it's like I can't bring a specific equation for the signal.
For non-deterministic, yes. Yeah. If it's deterministic, you have an equation.
I have an
In real world application, we can say that is like previously say is PCB signals. But for this random signal, what we can say is just a noise.
Well, for this, again, it's a coin. Okay? So you have a coin and you flip it. Okay? So you have no idea to predict what's going to be the result of the coin flipping. The only thing you can say it's going to be head or tail.
Yes.
It's bounded by the output. Okay? It's like when you have kids, it's only male or female.
For the coin example, we know that two outputs had okay. But for this case, how we know the outputs?
Oh, this is just my way of plotting head or tail. So 1 is head or tail, and -1 is head or tail. It doesn't really matter here. Okay. Got it? Okay. So statistically, you know that if you flip the coin, the probability of having head or tail is half. Right? That should be the case. Okay. Let's talk about kids, and then you have kids. Okay. So you have two possibilities, male or female. So the probability is half. But actually, you could have 3 males, or you could have 2 males and 1 female, or 5 females and 1 male. Okay. So locally, the probability is at 1/2. Okay. So the probability is defined on a much longer scale. Okay. This is why it's random. Okay. Random means the statistics that can describe the signal can be established on the long term. Okay. If you play lottery, you know, national lottery, like in every country you have that. Okay. If you look at the distributions of the numbers that were given every day of the lottery for like 20, 30 years, okay, all the numbers, they have the same distribution. They must have. Because otherwise, it's biased. It's impossible to have a number that has a much greater output than the other. Otherwise, there is a problem with the lottery. Okay? But this can only be computed for a long time. Okay? For a long time. I have another example, just a random signal. So this is just a random signal, the same type I use for my sine. Okay? And now what I'm going to be doing is plotting the way the values are distributed around 0. You have negative values, you can see. You have positive values. And you see that it's visual. The majority of the samples, they're here. Okay? And the minority of the samples, they're here and here. So you can imagine in your head, if you look at the way they are distributed, it's very dense in the middle and less dense on the sides. So if I plot the way they are distributed, and it's like an histogram. So So you have to count every time you have a certain value reaching a certain value. Okay? If I do this, that's what you obtain. And this is called a normal distribution. It's a Gaussian distribution. Okay? It's symmetrical. The main peak is located at 0, so it's unbiased. Okay? So that means the mean value of the signal is 0. Okay? And the width gives the variance of the signal. Okay? So you see that for my example here, you have almost 800 values with 0, or close to 0 at least. Okay? But this is a Gaussian distribution. Okay? You find Gaussian distributions everywhere in nature. Everywhere. Okay? The noise of the video projector. Okay? The height of people within a family is following the Gaussian distribution. Okay? If I take the age among you, it's going to be following a Gaussian distribution. Even when you have your grades, it's following sometimes the Gaussian distribution. Okay, so it's everywhere in nature, it's hidden. Okay, that's the way physics are built in. It's a built-in thing. Okay, so this is good to know that things follow this type of distribution. There are many other ones. Okay, but that's the main one that we use. Okay, because you can model it. Okay, so it's not deterministic because again you cannot predict specific values in the signal, but you have a model to plot the distribution. So you know that if you draw from the distribution, you can obtain a value, and the value is going to be on the red curve. Okay? So if you draw a value from the distribution, you will obtain a value that may be somewhere in this signal, but you don't know where. Because it's not deterministic.
It's a Gaussian distribution of the first signal.
Yeah. The blue is obtained from this, and the red is the theoretical model that was fitted on the data using Gaussian distribution. Okay. And that's it for that. It's a mistake. I think it's not the right place. It might change. Anyway. So if you look, this is just a summary of what we said. Okay. If you look at physical, yes. The question.
Can I go to the bathroom?
Yeah, that's something we need to discuss.
Okay.
Okay? Whenever you're in class, you stay in class. Just to be fair. Okay? You have to be on time, and I'll leave you guys on time. Okay? If you need to go somewhere for any reasons, okay? Let's say you have a phone call. I know you guys can have important phone calls related to your situation or whatever. You have to tell me before you expect a phone call. So whenever you have a phone call, you leave the room, you go back. Okay? You guys are adults, so I expect you to be attending the class for at least a couple of hours without going to the bathroom. Okay? Just to be fair. Alright? Because otherwise, it's complicated to manage. Okay? Is that okay with you? Yeah? You manage?
Maybe.
Maybe. If you feel you're not managing anymore, you can go to the bathroom. Okay, there's one just here. Okay? No problem. But for next time, try to be ready planning class without going to the bathroom in between. Okay? You will never see me leaving to the bathroom during class. Okay? Unless I'm sick. Alright, so here, in this class, we always deal with physical signals. Physical signals. Could be anything, but it has to be physical. Could be a current, voltage, anything, but physical. It's a real signal, it's not a fake signal. Okay? So again, we split these signals into deterministic signals, where you can have an equation defining them. I mean, you can define the amplitude of the signal for any time value. And then you have random or probabilistic or stochastic. This is another name, stochastic signals, where you just have a mathematical descriptions of the way the values distribute. Okay? But for a given time, you have no idea what's going to be the value. You have no idea. Okay? When you have a kid, I mean, it's impossible to tell before maybe the first or second echo. Okay? Right. So among the deterministic signals, you have the periodic and the non-periodic signals. So this is straightforward. Okay. So you can have in the periodic signals, you have the sinusoidal signals, and this is the main signal that we treat. Okay. And you could also have complex periodic signals like the square, the triangular signals. And among the non-periodic signals, even non-periodic signals can have some hidden periodicity within. So it's called pseudo-periodic signals. Okay? And then you have the transient signals among the non-periodic signals. Okay. And if I go back to the stochastic signals, you have two types, which I won't discuss much, but just for your culture. Okay? You have stationary and non-stationary signals. Okay? So what it means to be stationary means the basic signal properties of mean and variance do not change over time. So if you recall my distribution, okay, and if I was observing my signal for a long time, the distribution wouldn't change. Okay, it's stationary. So the fit I had in red wouldn't change. Okay, but if the signal is not stationary in time, the distribution will change. An example, let's say the video projector heats up, so it needs to cool down more with the fan, so the noise will increase. So it will change the noise value. So the distribution of the values over time will change. So this will be a stationary processing. Okay. Right now it looks like it's stationary because the noise power is the same. Okay. And among stationary signals, meaning the mean, the variance, and other higher order statistics will not change over time, okay, you have ergodic and non-ergodic signals. Okay. So ergodicity ensures that temporal averages, so if you take the average, okay, are identical to statistical averages. That means just looking at a small realization of the observation, you can fully understand the statistics. If it's non-ergodic, it's impossible to obtain the statistics from a few snapshots. Okay, you need longer snapshots. Right? So this is beyond the class, I would say, because for us, we'll only treat mostly deterministic signals, periodic signals, and we'll treat stationary signals that are ergodic in nature. I won't treat the other ones. Okay? Because it's easier. Noise, like this, sinuses, triangular signals, no, we treat. Okay? But we won't treat pseudo-periodic transient, we won't do that. Okay. Alright. So that's the first way of mind mapping the signals. And another way, and I'm sorry, I need to introduce some math. Okay, this slide. And you guys will be doing some math later on. Okay. So for a given signal, a physical signal, okay, that will be deterministic, mostly. Okay. we can define energy and power. Okay. So for you in your mind, I know it's fuzzy, and energy is the same than power, but it's not the same. Definitely not the same, right? So what's the difference between energy and power?
Energy is per unit time.
Yeah.
Power is simply it's not specific to time. It's just the how much energy it has.
I think so.
How can it consume this energy?
Yeah.
I think
energy is only consuming at that time.
Yes. Energy is power over time.
Yes.
Yeah. You can see that here actually in the definition of what is energy and what is power. Okay. Energy is a sum. Okay. It's a sum. It's an integral. Okay. It's a sum of a signal. Any signal. That is where you take the absolute value and you square it. Okay. And you integrate. Integrate means you sum all the samples over time. Okay, so you integrate that. And you integrate that with bounds going from minus 2 to t, where t can go to infinity. Of course, in our case, signals are never infinite. It's for theoretical sine or whatever, they are infinite. But when it comes to digital signal processing, they are not. Okay? So what I'm talking about for these definitions, I'm talking about continuous functions. Okay? This is for continuous functions. Right? So now if I look at power, power looks like energy, indeed, but you divide by 2. Okay? So indeed, in a way, it's energy over time. Okay? So if you think about your car, okay, your engine, it has some power, and the power can only be determined over time with the energy that is your gas. So gas is energy.
Yes.
Okay, and it gets transformed, okay, into the engine with a given power. Okay. So we say that the signal is an energy signal if and only if the energy is bounded. Okay, if it's bounded, it's finite. Okay, this is an energy signal. And for that case, if the energy is finite, because you divide by 2t going to infinity, the power goes to 0. Okay. We say that a signal is a power signal if and only if, and this is another definition, the power is finite. And for this case, if the power is finite, the energy is infinite. It has to be, right? Because of this. Okay. So it is also possible sometimes that a signal cannot be classified either as an energy or as a power signal. So depending on the cases, it's possible. Okay. So what I'm going to be doing is send you guys to the board. Sorry about that. I have snatched. Okay. And you have to try to work on these examples. So I have more examples that we treat next time. Okay, it's we do a guided session on treating continuous functions. We have to start with that. Okay, because maybe your math is a bit rusted. Maybe it is. So the idea is for you guys to go to the board. Okay, try to solve some equations. Okay. I can see eyes like this. No, not really. Alright, okay. It's gonna be fine. The idea is just for you to write down some equations and to try to to work out the old formulas that you learned in the past. Okay, and this is always useful. Okay. Again, you're a future engineer, so you need to work at math anyway. Okay. So the first example I have to give you is This example, I think I have it in my TD. So I can that. Do I have that in my class? So this is one of the examples that I have you in the TD. So TD is travaux dirigés, so guided work. Okay. So we can start with that one. It's fine. So the first example. Sorry, the board is not so large, so we have to deal with that. That's all it is. Okay, so the first example is one of t is a exponential minus a t ut. Okay, and the second example is a ut. Okay, so ut is a special function. Okay, it's called the step function. Okay, so the step function u of t is this. And this is u of t. It's called the step function. Okay, so for any values below 0, u of t equals to 0, and for any values greater than 0, it's 1. Okay. So 0. Okay. Okay. So this is the step function. Okay. So I'll treat the step function. Okay, we do it together. Okay, and then I send someone to the board for the first one. Okay. All right. So I try to compute the energy. So by definition, the energy it's always a limit when t goes to infinity of minus tt. So it's x of t squared dt. Okay. So you just substitute x of t with a u of t. So limit t goes to infinity. T of t is a u of t squared dt. Okay. A is a constant. It's positive. Okay. And because it's a constant, it's positive. You can put it outside of the limit. It's a constant. So you multiply it interval with a constant. So it's a squared. I can remove the absolute value because a is positive anyway. Okay. Limit when t goes to infinity between minus t and t of t squared dt. Okay. Now we have to observe what is u of t and see how we can change that integral with respect to the values of u of t. what we know about u of t is equal to 0 for t less than 0 and 1 for t greater than 0.
So the boundaries will change.
So the boundary change, so it's a square limit when t goes to infinity between 0 and t, okay? And we know that the value of u of t is what? What is the value of u
One.
of t? Is 1.
Yeah.
So it's dt. Okay? So it's a square. So what is the integral of dt of a constant? T, right? So it's a limit when t goes to infinity of t between 0
And t.
and t. And that's t. Okay? So t of 0, so it's equal to a square limit when t goes to infinity
T.
of t. Okay? Because you evaluate t at t and 0. Okay. So obviously it's gonna be the result of that is gonna be yeah, it has to be right. And do we need honestly to do that derivation to observe that it's an energy signal? No, because when you look at the signal, we know that the definition of energy is you take that function square and you sum over time for infinite values. And because this is constant, it goes to infinity. So you keep summing terms. So of course the output value is going to be infinite. It has to be right, just by looking at the nature of the signal. Okay?
So it's power signal.
The power is going to be different. Okay? Because when you compute the power, it is the same derivation, but the only difference is that you have 1 over 2t that appearing. Okay? So if you do this, so the power is the same. And if you wind up at the end, if you go to all the way down here, okay? So it's a square limit when t goes to infinity 1 over 2t, and it's going to be t.
Yes.
And you can simplify. So the limit is a squared divided by 2. So if you look at the definition, it is an energy signal because the energy is, it's a power signal, my bad, because the energy is infinite and the power is finite. So it's a power signal. Alright? Are we good on that? Any questions you would have on this derivation? So far so good? Not so good? Yeah. Okay. So don't worry, you won't be doing much. I mean, we'll be doing some derivation on integrals and stuff like that, but it's going to be very basic. I won't be doing advanced calcula or algebra. Okay, so something you guys know. If you don't know, I can be there to help you out. Working on this. No problem. I also have on Moodle, when you will be connecting and looking at the materials, you will be also find a sheet with formulas and trigonometry, because we will be using that. Okay. Whenever you deal with the sinus, cosinus, You will have to use Euler formulas and stuff like that. But this is the okay. So now, and I want to send someone in board. So it's an exponential function, but, and this is why I want to do the step function first, it's multiplied by the step function. And A is positive. Okay. So if I try to just draw the signal, we will be doing something like this. So, I won't be the first, but won't be the last. Otherwise, it's random. We are here to get trained on that. Okay. So, I mean, I don't expect you to succeed every time, but you're here to learn. Okay? And learning by failure is the best way to learn. Okay? Okay. So we're here to learn together. So if you don't succeed on the board, I mean, we can help you, etc. And this is the way you learn. That's the process of learning.
Okay, so first we want to start.
So you have to start with the energy definition. To get the complete energy.
Okay, we can take the group for each.
Yeah. Whenever you derive things, I prefer you guys to take it slowly. Make it one step at a time. Because when you skip lines, sometimes this is why you make mistakes. Take your time. Take your time. Okay. This is not math class. Okay, we apply math. You can do this, yeah. See? For a squared is a constant.
This class.
And u squared t, the step function square is a step function. It's the same. So in the end of the day, you have to integrate the exponential between 0 and t. And t. Because u of t, again, I have to be here, is bounded between 0 and t and t goes to infinity. And the value is 1. So we can just replace the bound. Don't forget the limit. There's always a limit. 0 and t of exponential minus 2 alpha t. Alright, so now this is why it's fuzzy. You need to recall how to compute the integral of an exponential. Sure. So it's here, on the left. So now you have a limit term.
So limit here becomes 0.
Yes.
And so we have this.
Yes. So the end result is a squared divided by 2 alpha. Thank you.
The power.
You want to compute the power? Go ahead. Compute the power. So this is a finite energy. So it's an energy thing. So you expect the power to be zero. If the energy is finite.
Because it's the limit
Yeah.
0 is.
Yeah.
So I can write it.
What you can do is just it's the same in here.
It's the same.
But you have 1 over 2t. Yeah.
When the integration become a little bit harder and included sine and cosine, there is trigonometry shape.
Yes, I will give it to you. Yeah, not from me, but from you. Okay. I want you guys to succeed, right?
Thank you.
I'm not interested into you for limit failing. So then, because you have exponential minus 2 alpha t divided by 2t, you know that the exponential form is stronger than the than 2t. Okay, so it goes to 0. Okay, and 1 divided by 2 alpha t goes to 0 also. So the whole thing goes to 0. So this is energy signal. Thank you. You good? So I will be giving you the exercise list next week, okay? And I expect you guys to walk ahead to the best of what you can, okay? I don't want you to do all the exercises. I will say, okay, you can do this and that. Okay, at least you have to try your own. Okay? So the idea is for you to, even if you don't make it alone, you can work in group. So I expect you guys to work in group, okay? And when we do it in class, we're going to be solving it together. At the end of the day, you will be enjoying them together. It's different feeling. We good on that? Any questions on this derivation? No? Okay. So I have 15 minutes left for the class, so I'm going to be talking about sampling multiplication. And the next time we'll be doing some exercises on that. Okay, just for your information. You got it? Not yet? So you also, something I didn't tell you about this class, that digital signal processing was invented very late. When do you think when was digital signal processing invented? Do you think? And practically implemented?
1960?
Yes, it's more or less in the middle of the 60s, I would say, because to do that we needed the transistors. Because the transistor is the main component that converts the currents into zeros and ones. Okay, so we needed that component invented by IBM, to make microchips that can handle digital signals. Okay. So the very first systems that were using digital signal processing, were in the end of the 60s and 70s. So it's not old, per se. Okay? Not old. It's only 50 years ago. 50 is nothing. Okay. Alright, so let's go back to the board. Okay. Now I'll be talking about how do we go from the continuous analog signal to the digital system. So if we start with the continuous signal, again, it's a trick, right? Because it's already on my machine, so it's already digital. But anyway, just for you guys, let's pretend it's an analog function. Okay, it's an analog signal. Okay, to make it a digital signal, we have to make two steps. These steps can be made alternatively or simultaneously. Okay. So the first step could be either the qualification of the signal, or it could be the sampling of the signal. Again, typically, both are done at the same time. Okay? So let's go with sampling, because it's easier to understand from that point of view. Sampling is, instead of having all the values in the time domain, I select specific values in the time domain. Okay? So I sample the signal with a given sampling time, okay? And the amplitude for these points correspond to my continuous function. Okay? So because it's a continuous function, the amplitude, its value is infinite also. Okay? The second step, once you have sampled the signal, means it's discrete in the time domain, but the values are continuous in the y-axis. Okay? The second step is to make it discrete on the y-axis. So to doing that, we use a codebook, dictionary. Okay? The dictionary transforms any continuous value into a discrete value. Okay? So any values, continuous values within a given range is given a specific discrete value from the codebook. Okay? And this is why we always talk about bits, because bits allows you to define a dictionary with a given number of values. Okay? So if you have a codebook with 1 bit, you have 2 possible values, 0 and 1, 1. So it's 2 to the n. Okay? If you have 2 bits, you have 4 values, etc., etc. Of course, the larger number of bits, the larger is going to be the dictionary. Okay? So, in terms of quantification, that means if your dictionary is very large, the difference between 2 adjacent numbers is very small. Okay? Think of it this way. If you try to define this signal with 2 bits, that means any positive value is 1, any negative value is 0. Okay? So the signal is going to be looking like something like this in the digital domain. With 2 bits. Okay. Now, if you increase the number of bits, again, the step between values is going to be very small. It's going to be very small. Okay. And that means for any given value that is continuous in the y-axis, you have a mapping table given by a dictionary that gives you the equivalent value in the discrete domain. Okay? So, just for example, with 4 bits, or maybe I can do with 2 bits because otherwise you can spend a long time on that. So 2 bits, you have this. These are all the possible combinations. 2 bits, okay, and you have 4 values. Okay. So if you have a signal, let's say you have a sinus that is bounded between -1 and 1. Okay, what does that mean? That means you can say arbitrarily that this is between -1 and 0.5, and -0.5. This is between -0.5 and 0. This is 0.5, 0.5, and 1. Okay? So any values, continuous values between -1 and -0.5 will be given as 0, 0. Any values between -0.5 and 0, 0, 1, etc. Okay? Of course, when you increase the number of bits, the difference between these values will get smaller and smaller and smaller. Okay? Makes sense. And actually the step, if you compute the step here, Q defined by this, function, where n is the number of bits. Okay. Of course, when n goes very large, Q goes down. So okay, we say, okay, what's a good value for n? Is it 2? Is it 1000?
64.
Why? Why not? The problem is, now you have, let's say you take 64, okay? You need something, a device, that converts this in a 64-bit manner. It doesn't exist. That doesn't exist right now. It's impossible. Okay? Right now, the converters, I mean, the analog to digital converters that you have in your phone, or digital to analog converters that you have in your phone, they're between 12 to 14 bits. That's it. Why? Because the number n determines the speed at which you do the conversion. So if you want to have a very, very, very small quantum step between values, it's going to be taking an infinite time to do that in terms of conversion. Okay? And this is going to be very expensive. Okay. Right. So you have to find a trade-off. So that's also a limitation of digital signals. Because the first trade-off is you need to sample the signal. So imagine you walk in a car factory. Okay? You're on the chain and the car is on the traveling belt. And you have to do the operation as fast as possible on the traveling belt. Okay? So when the traveling belt, the speed is small. You have the time to do the operation, so you can select, you can do your operation. But what's happening when you increase the speed? At some point, it's not possible to do the operation. Okay? So the hardware that you have is the same. There's a limitation on the speed at which you can sample the signal in time. Okay? So you have two limitations: sampling time and qualification. And it's a trade-off. You can be very fast, but with low bits. You can be very slow, with a high number of bits. So it depends on the nature of the signal and how you process the signal. Okay? For example, if you work with audio on your phone, it's for the audio it's 16 bits. For the radio, it's between 12 and 14 bits. Why 16? Because 16 is the highest resolution that your ear can distinguish. Meaning if you increase the number of bits, you won't feel the difference. Okay? So it depends on the application, it depends on the target. Okay? But typically you have to recall that going to larger number of bits, it doesn't help on the hardware implementation. It's going to be very costly, very extremely costly actually. So that's why when it comes to smartphones, integration and cost of devices, you want to achieve good processing without the need to be implementing very high bit systems. Okay? And in the end, when you combine these two operations, sampling in time, qualifying on the y-axis, you obtain the digital signal. Okay? So in your phone, the converter that is being used to receive the electromagnetic wave from the Wi-Fi or 4G, 5G, whatever, okay? You have the antenna that receives it, converts into current and voltage, and then you have the converter, the analog to digital converter that will perform this operation for you at the same time. Okay? But this is the way we decompose it because it's easier to explain. Alright? So in the end you have a digital signal that is stored and can be processed. Okay? And of course, again, what is important to remind you guys is that the processing that is being done, okay, it has to be done accordingly to the number of bits and the sampling time of the signal. And we'll see that a bit later. And I think I'm done for today because I want